So hopefully after going over those examples and seeing those visualizations, you have a better understanding of what the sampling distribution is. Hopefully you also understand that the sample mean should be treated as a random variable because of the random process that leads to the samples on which we calculate a sample mean. All right. Finally, you should be aware that the central limit theorem gives us the shape, the mean, and the standard deviation of a sampling distribution, or of the sample mean random variable. Since we know how the sample mean random variable will behave as a random variable, we can use that information to start answering real-world questions. So what I want to do next is focus in on some practical applications of the central limit theorem. We'll be using it further for inferential statistics, but for now, I just want to focus on a particular application. That application allows us to extend some of our probability analysis to working with groups of scores rather than individual scores. Right? So the analogy here is that the population is going to be a random variable that measures a single individual score. When we start looking at groups of scores, we're going to be using the central limit theorem because the new random variable we'll be talking about is the mean of a sample. So for all of the examples that are about to follow, here are the guiding questions. Is the probability in question about a single score or measurement? If so, we're not going to use the central limit theorem. We're going to use our original probability distribution. On the other hand, if we have a different answer to that question, is the probability asking about the mean or the total of a group of scores or measurements? In this case, since we're talking about a group, right? A group is another word for a sample. So we're really talking about a sample mean or a sample total. And anytime we're talking about a sample mean as a random variable, we need to apply the central limit theorem. So before you start any type of probability question, we're going to think to ourselves, is the probability talking about a single measurement, or is it grouping a collection of measurements and computing a mean or a total? And this will tell us whether or not we need to use our central limit theorem in solving our problem. Okay, I think we're ready to start considering some examples. All right, so here's a nice setup. We're inside of our W7D2 Excel sheet, and I've clicked on the sheet that says CLT example 1. So here we're going to see a practical application of the central limit theorem. Here's our setup. Suppose the monthly returns on our investment portfolio are normally distributed with a mean of 1,000 and a standard deviation of 300. Okay, so the idea here is we have some investment portfolio. Each month we get some money back. These are our monthly returns. And each month we know that the amount of money that we get has a nice normal distribution where the mean is 1,000, so that's sort of the most likely value. We're closest to that value. And there's a standard deviation of 300. So our usual range of scores, remember, would be 2 standard deviations in either direction. So that would be about $400 up to $1,600 is the usual range of returns in a given month. Here's what we want to know. We want to, first of all, find the probability that our return next month will be greater than 850. So ask ourselves our motivating questions. Is this probability in question 1 talking about a single score, or is it talking about the mean or total for a group of scores? We'll repeat the question again. Find the probability that our return next month will be greater than 850. So think about these motivating questions. Do we need to apply our central limit theorem here? You might want to pause the video, take a guess, and then we'll see if you're correct afterward. Okay, so in this case, we do not need to apply our central limit theorem. The reason is we're finding the probability that the return next month, this is one monthly return, right? So this is a question about a single score, and we know that we do not use the central limit theorem when we're dealing with single scores. So no, this is a probability about one monthly return. Okay, so what's our directions? If we're not going to apply our central limit theorem, the idea is to use the original probability distribution to answer our question. So in other words, since we know that a single monthly return is normally distributed with these parameters, we can follow through, write everything out symbolically, and use our norm.dis to find our answer. So here, if we want to know what's the probability a single monthly return, so this is just going to be, let's call it x, is greater than 850, right? That's how we would write it symbolically. Looking at it, it's not going to be cumulative, so I recommend that on your own you draw a picture of your normal distribution, and keep in mind that we're shading in this case to the right. So we have to apply our 1 minus trick in order to find this probability. And now once we've applied our 1 minus trick, we know that we're dealing with a 1 minus a cumulative distribution. We know here that x is normal with a mean equal to 1,000 and a standard deviation equal to 300. So we can use our norm.dist to compute this probability. 1 minus norm.dist. The score we're dealing with is 850. Our mean that we're dealing with is 1,000. And our standard deviation in this case is 300. Right? We haven't updated any of the provided parameters because we're not applying the central limit theorem. Right? So our final answer here, the probability that our return next month is greater than 850, is going to be about 0.691. Okay, now let's go to our second problem. Find the probability that the average return over the coming year will be between 950 and 1105. So once again, we want to revisit our motivating questions here. Is the probability we're interested in, is this about a single score or measurement, or is it treating a group of measurements by either taking the mean or counting up the total? So returning to our problem, let's find the probability that the average return over this coming year will be between 950 and 1105. So pause the video, again, take your educated guess, and see if you get the right answer. In this case, we're talking about a group of scores. Keep in mind, if you're looking at the average return over a year, this involves 12 monthly returns, right? Moreover, right in the problem, it's mentioning the fact that we're dealing with an average, right? Find the probability that the average return over the coming year will be between 950 and 1105. So this average, I'm going to call it x bar because it's hard to draw an x or a bar over an x inside of Excel. This is going to be the random variable that represents the average return over 12 monthly returns. So this tells us that we're working with a group, an n value of size 12. So what we want to do here is take a look at our central limit theorem and apply it. So keep in mind, our central limit theorem says that mu of x bar is the same thing as our original mu, but sigma of x bar, this group mean estimate, sigma of x bar takes your original sigma and divides by the square root of your sample size, which in our case is 12. So we absolutely do have to apply our central limit theorem in this case. Hopefully this makes sense. And before we move forward, we need to actually compute what is mu of x bar. That'll be easy. And more importantly, what's sigma of x bar? What's the new set of parameters for this normal random variable treating the mean across 12 of these observations? So, what we know from our central limit theorem, if I can back up a little, what we know from our central limit theorem is that the means between your original random variable x and the sample mean should be the same. So if our mean for the original random variable is 1,000, the mean for our group mean random variable is also 1,000. The standard deviation, however, changes. Where previously our standard deviation for a single return is 300, when we group 12 of them together, we have to adjust the standard deviation by dividing by the square root of our group size. So we have a new standard deviation, 86.6, that we're going to use to answer this problem. Right? Once you have your updated parameters, right? These are important. Once we have our updated parameters, now we can just return to our usual normal random variable analysis to answer the question. We want to know what's the probability that x bar, so this is an average return over 12 measurements, is in between 950 and 1105. Now we notice right away these are not cumulative because we sort of cut ourselves off at the end. And our typical trick for dealing with this is we take the cumulative distribution for the larger one and we subtract off the cumulative distribution for the smaller one. Okay? Now each one of these is going to have its own norm.dist as we normally see. Norm.dist 1105. But when we talk about the mean and the standard deviation, we're going to plug in our updated parameters. So I'm just going to cell reference them here. I have my mu x bar and my sigma x bar that I'm plugging in for those values for my norm.dist. And I'll do the same thing when I'm subtracting off the cumulative associated to 950. I'll cell reference my new updated mean and standard deviation and true. And this will give me the appropriate answer. So keep in mind, when I'm talking about x bar, I need to update my parameters according to the central limit theorem formulas, right? Mean stays the same, but standard deviation takes your old standard deviation and divides by your square root of n. So that's what we did in this cell. And now when we apply our norm.dis using our usual normal random variable analysis, you just have to make sure to feed in those updated parameters. The other thing that I want to point out is it's important to judiciously use x versus x bar when you're talking about these parameters, or when you're talking about these probabilities. If you're talking about a single score, you're just going to use x. When you're talking about an average return, you want to use x bar. And keeping these two notations separate, x versus x bar, will allow you to remember when you need to update these parameters, right? When you need to update your sigma x bar, your standard deviation, when you're applying your norm.dists. Okay? Let's consider our last question. Find the probability that the total amount of our returns over the next 6 months is less than 7,000. Now this one is a little bit tricky, but first let's just get started with our motivating question. All right? Is the probability that we're considering a single score, or is the probability we're considering referencing a group of measurements somehow collected together as either a mean or a total? So reading through the problem again, find the probability that the total amount of our returns over the next 6 months is less than 7,000. So make your guess, pause the video, and we'll see if you're right. Okay, so there's 2 clues in this case. The first clue is that we're dealing with a total. The second clue is we're dealing with returns over the next 6 months. Right? So it's not just a single monthly return. We're dealing with 6 of these monthly returns. But rather than measuring their mean, we're actually looking at their total value. So since we're still dealing with a group of scores, which we're somehow aggregating into one measurement, we do have to apply the central limit theorem. So we are still working with a group of scores. So CLT needs to be applied. However, not directly. We need a trick. Okay? So what is our trick going to be? Well, let's think about what a total would be. All right, a total might be 1 monthly return, 2 monthly returns, 3 monthly returns, 4 monthly returns, etc., etc., etc. All right, so essentially we've measured this random variable 6 different times. We're looking at their sum. Now, if you think about what x bar would cover, it would essentially be this same collection of random variable measurements. It'd be this same collection of monthly returns. All right, so this would be x1 plus x2 plus x3, et cetera, except if we're dealing with a mean, we do something at the end. When you're dealing with x bar, you essentially just end up dividing by 6. So this leads to the general idea that a mean, x bar, is just going to be a total divided by 6. So if we start writing out the probability of concern in this particular case, we can always change it over to a probability in terms of x bar, where we can apply our central limit theorem by just dividing by the sample size in question. Okay? So first of all, our group size, or our n value, is equal to 6. Now the probability we're interested in is the probability that the total, so this is all the 6 returns added together, is less than 7,000. All right. Now keeping in mind that the total divided by 6 ends up giving us our x bar, an equivalent way of writing this, and it's sort of like the same way that you change a measurement on x into a z-score measurement, a different way of writing this would be to just divide both sides of your equation by 6. And the interesting thing is that we know that if you take a total and you divide it by your sample size, this just gives you x bar. So the question is, what's 7,000 over 6? Well, that's something we can compute. If we just pull off a cell in Excel and divide 7,000 by 6, we end up with this equation, 1166 point, let's call it 67. And this is the new random variable, or this is the preferred random variable to work with, right? Here, now that we're in terms of x bar, we can use the central limit theorem. Does this make sense? So this trick, this observation that the sample mean is really a total divided by your sample size, allows you to take probabilities about a total and change them into probabilities about a mean. The idea is just divide everything out by your sample size. So take these numbers provided and divide them by your sample size, and you'll get an appropriate question about x bar itself. Now, as we saw above, we need to adjust the mean and the standard deviation according to our central limit theorem. As we've mentioned before, we know that the mean and the standard deviation are governed by formulas. Our mean specifically doesn't change. So since our original single monthly return had a mean of 1,000, this mu x bar is still going to be 1,000. Sigma x bar, as we mentioned before, is just updated by your old standard deviation divided by your sample size. Right? So in our case, our old standard deviation was 300, but what we want to do is divide this or modify our standard deviation by dividing by our sample size. Here, since we're only concerned with the next 6 months of returns, our sample size is 6, so we would divide the standard deviation by 6. So this gives us a sigma x bar equaling 122.47. Right? Now that we have our probability and the appropriate parameters, we can just follow through the rest of the problem by using our normal approach with a normal random variable. So the first thing you check is this thing in a cumulative form? It is already cumulative, so we can jump directly to applying a norm.dist, where we use 1166.67 as our score, 1,000 as our mean, an updated standard deviation, so this is according to our central limit theorem, and then true. So our probability in this case ends up being 0.913 roughly. So this is the approach. When you're dealing with a single return, you don't apply the central limit theorem. In other words, you do your standard normal analysis, but with the provided parameters, 1,000 and 300. When you start working with averages for a group, you're now dealing with the x bar random variable. right? This is a mean random variable for a group of a certain number of scores. The mean for your x bar stays the same, but your standard deviation for the x bar gets updated. So in this case, you have to divide by the square root of your sample size. Once you have these new parameters, you do your standard analysis, make everything cumulative, and apply your norm.dists with these updated parameters. Finally, if you're dealing with a total, you have to do a little trick first. You have to take the probability of the total, so this is coming directly from your problem. You divide out by your sample size on both sides, and this ends up giving you an equivalent statement about a probability on the mean. Once you have the probability on the mean, you can compute your two new parameters, and then proceed using a norm.dists approach, again with these updated mean parameters and the updated measurement and the updated score. Okay, so what I want you guys to do now is pause the video, and I want you to look at CLT example 2. Right? The first thing I want you to try is go through, read each problem carefully, and take your best guess. Are we going to apply the central limit theorem in these cases? And just put a yes or a no, and if you can, maybe a little explanation. Okay, let's see how you did. So in our first case, we want to, for question number 1, we want to find the probability that the mean upkeep charges for all company computers is above 95. So first of all, there's two clues. First of all, we're talking about the mean upkeep charge, which should be sort of a red flag. And we're also referencing all company computers, right? And if we're looking at all company computers, we're not dealing with a single computer, but a group of computers. So the correct answer here is yes. We're absolutely going to have to apply our central limit theorem because we're dealing with a group. Now, luckily, it's talking about a mean, so we'll be able to use the x bar random variable directly, so we don't have to apply any tricks like we did with the totals. Let's consider our second one. Find the probability that the upkeep for the CEO's computer is less than $115. Now, in this case, there's a couple of hints. First of all, we're talking about a single person's computer, and this computer is singular, right? It's not plural. This is one computer that we're referencing. So we're asking about the upkeep charge for a single computer. Because of that, we don't need to apply our central limit theorem. The CEO has one computer, single measurement. So in those cases, we do not apply the central limit theorem. We just use our original distribution, and that's the one that's provided in our problem up here. Last case, find the probability the total upkeep charge for the company's computers this year is between $6,825 and $7,800. In this case, again, there's two clues. The first is that we're referencing a total, and the second is that we're referencing the upkeep charge for the company's computers, plural, right? So we're dealing with a group of computers. The company, of course, owns 65 computers. So what we're referencing here is a group of, again, size 65. Okay? Now, since we're dealing with a total, we will need to eventually divide our provided scores by the sample size to get an equivalent statement about x bar. So this is just looking forward a little bit. So we now have a rough game plan for how we're going to approach this. For problem 1, we know we're dealing with a group of size 65. We have to apply our central limit theorem. And so we're going to find our x bar, which would be the mean upkeep charge for a group of size 65. We're going to find its parameters, mu x bar, sigma x bar. And then we're going to proceed using our usual norm.dist approach. For number 2, we don't have to do any updating. We're not applying the central limit theorem, so we're just going to use our original parameters of 145 with our norm.dist approach to answer this problem. For our last one, for number 3, we're dealing with a total. So we're going to take these numbers, the 6825 and the 7800, we're going to divide by our sample size and write this equivalently as a probability statement about the sample mean. Then we'll find our parameters, mu x bar, sigma x bar, and we'll again, approached by doing our normal norm.dist analysis. So with that guideline in place, what I'd like you to do is to pause the video again and inside your own Excel sheet, try these out on your own before I go over them and see how you do. Okay, let's go over these final 3 examples. So in our first case, we want to find the probability that the mean, so we're dealing with the x bar random variable, the mean upkeep for, in our case, all the company's computers. And reading from our problem above, we assume our company owns 65 laptop computers. So we're dealing with a group of size 65. So we might do our n value equal to 65. So we want the probability that the mean upkeep for these 65 computers is above 95. Now in this case, since we're dealing with x bar, we need to find our new parameters according to our central limit theorem. Keep in mind, yes, we are applying our central limit theorem here. So what's the mean of the x bar random variable? According to the central limit theorem, this shouldn't change at all. It's the same as the mean that we would see for a single computer. So this is still 100. However, the standard deviation for our x bar random variable does have to update. This takes our old standard deviation, or the standard deviation for a single computer, 45, and it updates it by dividing by the square root of our sample size. So in this case, we would divide by the square root of this 65. So now we know that the standard deviation for this group of 65 is more like 5.58. So we can proceed, now that we know the parameters for x bar, using our standard approach with norm.dist. The first thing we would do is turn it back into a cumulative distribution. Since we're doing a greater than in this case, we apply our 1 minus trick. And again, I suggest that you draw your pictures associated to this. It's difficult for me to do that in a screencast. But you should be drawing your pictures, labeling your axis with your measurements, shading in the appropriate directions, and using all of that to arrive through your norm.dist analysis process. Now, we want to take 1 minus, and since x bar is less than 95, we're going to do norm.dist. We'll use our score 95. We use this mu of x bar, which is the same as our original, but we use our updated standard deviation. So sigma of x bar is our new standard deviation, and then true. This will give us our final answer. This is our probability that for the group, the mean is above $95. So there's a pretty good chance of that occurring, 81%. For number 2, we want to find the probability the upkeep for a CEO's computer is less than 115. So notice that in this case, we're only dealing with a single computer. So rather than using x bar, which is the random variable that we use for a group of measurements, the mean for a group of measurements, since this is just the upkeep for a single computer, we just use x. So when we write this symbolically, we just want the probability x is less than 115. Now x's parameters, which we could write mu of x and sigma of just x, right? These were provided in the beginning as a mean of 100 for a single computer. We had a mean of 100 and a standard deviation of 45. So we can use these parameters directly in our norm.dist. Since this is already cumulative, right? We're shading to the left in this case. We just go directly to norm.dist. We use our score of 115. The mean is 100, and the standard deviation is 45. We indicate that cumulative is true. That's always the case for these norm.dist problems. And now we hit enter. This is our probability for problem 2. So there's a 63% that the individual computer, the CEO's computer, has an upkeep charge less than 115. Okay, last but not least, this one involves a little trick before we can apply our central limit theorem. So notice that the probability that we're asking about here is a total upkeep charge, right? So written symbolically, we might do something like this. What's the probability that the total falls in between 6825 and 7800? Now, unfortunately, CLT only applies or only gives us formulas for x bar as a random variable. It doesn't give us formulas for the total, but there's a little trick. Keep in mind, in general, x bar is really just the total divided by your sample size. So in this case, it's going to be our total divided by our sample size of 65, right? We have 65 laptops grouped together. So we're dealing with an n value of 65. So what we can do is write this as 625 over 65. Divide everything through by this sample size. And the effect is that on the inside, this is going to simplify to x bar itself. And on the outside, we can actually find what 6,825 over 65 is equal to just by using a cell to compute that. In this case, it ends up being 105. If we do a similar computation for our upper bound, we'll get 120. So this whole thing simplifies to the probability that our x bar random variable is in between 105 and 120, right? And the nice thing about this is that the x bar random variable is the one that we know we can use our central limit theorem with. Okay, so what we're just going to do is take this probability, 105 less than x bar less than 120, and we're going to do our normal central limit theorem approach with this. Right, so x bar represents the mean for 65 computers. Right, so it's our sample mean for a group of 65. The expected value of that, or the mean of our x bar random variable, is the same as that for a single computer. That's what our central limit theorem tells us. The means don't update. What does have to change is your standard deviation. And the way that you change your standard deviation is you take your old one, so our old standard deviation was 45, and you divide that by the square root of your sample size. And in this case, our sample size is 65 because we have 65 computers. So to compute this, I need to start the cell with an equals, but this would give us our new standard deviation. You'll notice it's the same as in our question 1, and this is because the group size, the total number of laptops at the company is remaining consistent. All right, so now that we have the right parameters, this is a norm.dist approach. We have to first change them into cumulative distributions, and then we can apply norm.dists with these updated parameters. So using the standard trick for in-betweens, this will be x bar less than 120 minus the probability that x bar is less than 105. And then each one of these is going to get a norm.dist. So we'll have norm.dist, 120 is my score, mean of 100, standard deviation, my updated parameter, true. That takes care of my first cumulative. Now I can do norm.dist. My bottom score is 105. My updated mean, well, not really updated, but the mean for x bar. My updated standard deviation, this was truly updated, and then true. This gives me my 2 norm dists for each cumulative probability here. And now when I hit enter, I end up with the probability of this occurring. So there's a 18.5% chance that if we look at the total upkeep charge for the company's computers, it's going to fall between 6,825 and 7,800. So this is how we apply the central limit theorem into practice. Any time that we're dealing with a group of scores, and we can summarize that in 2 ways, either with a mean, right, the mean for the group, or with a total, the total for a group, we need to apply our central limit theorem, which essentially means at the end we'll be working with an x bar random variable, a sample mean random variable. This sample mean random variable is normally distributed, but the mean remains the same, but its standard deviation is going to get smaller. We have to adjust this by dividing by the square root of our sample size. Once we have these new parameters, we can use our norm.dist approach to find the appropriate probability. Now, if it happens to be that we're asking a question where you're only dealing with a single computer, so you're not trying to summarize a group in any way, here you just use your original distribution that was provided. Normal distribution, so norm.dist, mean of 100, standard deviation of 45. So for one measurement, you just use the provided measurements, or the provided parameters. You don't have to update your standard deviation. You use the one that's provided. Okay? But all of this in the backbone depends on using your norm.dist analysis, which is why that's so important. Changing things to cumulatives, knowing how to plug in the right norm.dist commands, that's critical. But the added twist is that now you have to be able to discern whether you're talking about a single score, where you would use x, or the mean for a group of scores, where you'd use x bar and apply the central limit theorem. And this is the main content and main application of central limit theorem that we're going to see until we start talking about confidence intervals and eventually hypothesis tests. So for now, this is where we'll stop.